Right, so today we're going to talk about momentum and impulse. First of all, what is momentum? Momentum is the quality of motion an object has. The way you want to think about it is it can be defined as mass in motion. Anytime an object is moving, it is going to have momentum. And the momentum can also be thought about how difficult is it going to be to stop a moving object. Again, only moving objects have momentum. And the more momentum that it has, the more difficult it's going to be to stop. So the momentum of an object is dependent upon how large the object is, how fast that mass is moving, and those two combined, if you have a small object moving slowly or a large object moving slowly, they're going to have different momentums, but the higher your momentum, the more difficult the more difficult that object will be to stop. Now, it's not, because it is based upon those two things, both mass and velocity, you can have a very small object, for instance, like a bullet, that is moving at a very high velocity, is going to have a very large momentum. Or you could have a supertanker that is a huge mass, but if it has a small velocity, then it's going to have a lower momentum. And again, even if you have something like the supertanker, if it is attached to a dock and not moving at all, then even though it is this giant object, its momentum will be 0. So we have a new equation. Our new equation is momentum is mass times velocity. The symbol for momentum is actually P. It's going to be coming from a Greek word, which is why it's P and not M. And also we can't use M because M is mass. So we have P equals mv, which is momentum is mass times velocity. And we have an awkward unit here, whereas all of our other units are just like one word or one letter. Momentum, there is no special unit for it, so instead it is just kilograms meters per second, because we are multiplying the mass, which is going to be in kilograms, times velocity, which is meters per second. So we just combine those two to make the unit for momentum. Momentum is a vector quantity, so again, direction does matter. Momentum can be positive and it can also be negative. So let's do a practice problem. What is the momentum of a 75 kilogram speed skater that's moving forward with a velocity of 16 meters per second? The first thing we're going to want to do, as always, is list our variables, list what we know and what we don't know. We're trying to find the momentum. We are given the mass and we are given the velocity. So then I'm just going to plug those into my equation. P equals mv. So momentum equals 75 times 16. Plug and chug, and I get that his momentum is 1,200 kilograms meters per second. Go ahead and pause the video and give this one a shot. Okay, so we have momentum is what we're trying to find. We have the mass of the car is 1,500 kilograms. And since the car is moving to the west, we're going to make that -2 meters per second. Again, plug and chug, and we get the momentum of -3,000 kilogram meters per second. All right, so now let's start talking about changing momentum. Anytime that there is an object either changes its velocity, meaning changes direction, changes its speed, or if there's a change in the mass. So say for instance you're pulling you're pushing a shopping cart and then one of your friends jumps onto the side of it, you're going to have a change in mass. In either of those situations, you're going to have a change in the actual momentum of the object. So we now have the second equation here, which is delta P. Remember, delta means change in, is your final momentum minus your initial momentum. Okay, now we can actually expand this equation here, and we could have that delta P equals mass times your final velocity minus mass times your initial velocity, or your starting velocity. These are the same equation. Even though they look different, they are the exact same equation, okay? So this is the expanded form. The equation in red is the expanded form of the equation, the delta P equation. So, for example, we have a scenario where there's a car, a 1,200 kilogram car traveling east that speeds up from 25 meters per second to 40 meters per second. So again, first thing we're going to do is list our variables. We're trying to find the delta P. We're trying to find the change in momentum. So that's the one we don't know. Our initial momentum is going to be the mass times the initial velocity. So that's 30,000 kilogram meters per second. My final momentum is going to be the same mass, because the mass of the car in this situation does not change, times the final velocity, excuse me, which is 48,000 kilogram meters per second. Now I can plug those two values into my equation. So I'll have change in momentum is 48,000 minus 30,000. So the change in momentum is 18,000 kilograms meters per second. Now the change in momentum is positive because the velocity is increasing. So it is increasing in speed, therefore we have a positive change in momentum. Okay, so go ahead, take a second and see if you can pause the video, see if you can complete this practice problem. All right, so we have the same situation. We have a change in momentum of an 8 kilogram object moving forward. It goes from 40 meters per second to a complete stop. I'm trying to find my change in momentum. My initial momentum is going to be 8 times 50, because that's how quickly it was going in the beginning. So it's 400 kilogram meters per second. My final momentum is going to be 8 times 0, because it went to a complete stop. So 0 kilogram meters per second. And when I plug that in, I have 0 minus 400. So my delta P is negative 400 kilogram meters per second. And it's a negative value because it is slowing down. The object is slowing down and coming to a stop. Therefore, I have a negative change in momentum. All right, momentum, or change in momentum and impulse are connected. So in order for a momentum to change, there has to be a change in the force that's applied to the object over a certain amount of time. So for instance, if I'm driving in my car and I want to slow my car down, I have to push the brake. The brake applies a force to the wheels, which slows the vehicle down. So there is a force that is applied, and depending upon how long and how much force I use to push that brake, how hard I'm pushing the brake, and for how long I push the brake will determine how much my momentum changes. Like if I just tap my brake, I'm just going to slow down a little bit. But if I hold the brake down for a long period of time, then my momentum, my speed, and therefore my momentum is going to change more drastically. So this idea here is called impulse. And we have the symbol J is the variable that represents impulse. The unit for impulse is the same as the unit for momentum, or change, yeah, same as the unit for momentum, kilogram meters per second. An object's impulse is the same value as the object's change in momentum. So delta P and J are the same value. Okay? So the amount of time that you take to cause a change in momentum is going to determine how much force you need to make that change. So in this example, we have an example from baseball. If you're a catcher and you're catching a fastball and you leave your hand, you have your hand stiff, like your elbow is locked. When that ball hits the glove and it goes from a high speed moving object to being stopped in the hand, the catcher is going to feel a lot of force. Whereas if the catcher gives with the ball, meaning it takes more time for the object to actually stop, the amount of force that they're going to feel is going to be less. Another way of thinking of it is, again, if we're in a car and I have to stop, like if I go from 50 miles an hour on the highway and like suddenly I have to stop really quickly because another car in front of me stops or somebody swerves into my lane, I have to push my brake much harder than if I want to slow down to a stop over a long period of time. So impulse has a time component, and the amount of time is inversely related to the amount of force that's needed. So if I want to change a momentum of 100 kilogram meters per second, the longer I take to make that change, the less force is required. The faster I want that change to happen, the more force is required. Okay? And just remember, impulse is change in momentum. So this is our final equation for the notes today, which is that impulse equals force times time. Okay? Impulse equals force times time. So let's do a practice problem here. Okay, we have a 40 Newton force applied to an object for 5 seconds, and I want to find the impulse of that object. Again, list my variables. Impulse is what I'm trying to find. I know it's a 40 Newton force, and I know it's going to take 5 seconds. So I plug it in, and I get that the impulse, or the change in momentum, because again, they are one and the same, is 200 kilogram meters per second. All right, so let's take both of the equations and kind of see how they are going to work together, how we'll use them together. So in this problem, I have the question of how long must a tow truck apply a force of 550 newtons to increase the speed of a 1,200 kilogram car from rest to 2 meters per second. In this case, I'm going to use the fact that impulse equals change in momentum, and change in momentum is your final momentum minus your initial momentum. So I'm going to get to that in just a second. But the other information that I also have is that the force is 550 newtons. And then what I'm trying to ultimately solve for is time. So finding my initial and final momentums, I'm going to take my initial momentum is 0 because it's 1,200 because it's at rest. So it's a 0 velocity, therefore 0 momentum. And I have my final trying to get it to 2 meters per second. So it'll be 1,200 times 2, so 2,400, which means when I solve that, I get 2,400 minus 0 is 2,400 kilogram meters per second. So that is my impulse. Now to solve for time, it's going to be impulse divided by force. I know that my impulse is 2,400. My force is 550. Therefore, it would take 4.3 seconds with that amount of force for the tow truck to get that car moving from rest to 2 meters per second.